Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual landscape of the mid-19th century was one of burgeoning specialisms, where thermodynamics, chemistry, and optics pursued increasingly independent trajectories. Into this environment, Gustav Robert Kirchhoff's 1860 paper, formerly titled On the Relation Between the Emissive and Absorptive Power of Bodies for Heat and Light, arrived as an act of profound synthesis. This document, a cornerstone of what would become spectral analysis, did more than present new findings. It constructed a complete theoretical edifice, starting from a foundational abstraction, proceeding through rigorous thermodynamic logic, and culminating in an experimental proof of almost theatrical elegance. Its conclusions redefined the nature of light from celestial bodies and handed chemistry, a tool of unprecedented power. This essay will undertake a direct and systematic evaluation of the internal claims presented within Kirchhoff's 1860 work, proceeding section by section to analyse the logic, evidence, and conceptual frameworks that he so masterfully assembled. We will trace the argument from its theoretical origins to its grand cosmological and chemical assertions, assessing the coherence and strength of each intellectual step as presented by Kirchhoff himself. Section 1. The postulation of the perfectly black body. Kirchhoff's argument commences with a conceptual maneuver of immense strategic importance, the definition of a perfectly black body. This is a theoretical construct, an idealized object that completely absorbs all incident radiation of any wavelength at any angle. The paper's initial claims revolve around the necessity and utility of this abstraction. Kirchhoff posits that to understand the universal laws governing radiation, one must first conceive of a body whose radiative properties are independent of its particular material composition, shape, or surface texture. The black body serves this exact purpose. The claim here is one of methodological essentialism. He argues that only by examining the behaviour of such a perfect absorber can the fundamental relationship between emission and absorption be isolated from the confounding contingencies of real-world materials. His evaluation proceeds by demonstrating that any body in thermal equilibrium within an enclosed cavity must behave in a specific way, and the properties of the cavity's radiation itself can be analogized to the radiation of this ideal body. The validity of this initial claim lies in its power to simplify the problem to its absolute core. By creating a theoretical baseline, Kirchhoff establishes the conditions for a general law, moving the study of radiation from a collection of empirical observations about different substances into the domain of universal physical principles. The internal logic is impeccable. The postulation of the ideal case is the necessary prerequisite for the derivation of a law intended to govern all cases. This act of intellectual purification sets the stage for the entire theoretical development that follows. Section 2. The thermodynamic derivation of the emission and absorption law. Following the establishment of the ideal black body, Kirchhoff presents the central theoretical claim of his paper. He argues for a fundamental relationship between a body's capacity to emit radiation and its capacity to absorb it when in a state of thermal equilibrium. He frames this through a thought experiment of crystalline clarity. Imagine an enclosure with perfectly reflecting walls, maintained at a constant temperature. Within this enclosure, bodies of different compositions are placed. Through the principles of thermodynamics, specifically the second law as understood through the work of Clausius, Kirchhoff asserts that all bodies within this space must eventually reach the same temperature as the enclosure. For this equilibrium to hold, each body must emit precisely the same amount of energy that it absorbs. He then refines this claim by considering the radiation on a wavelength-by-wavelength basis. He defines the emissive power, represented as a capital letter E, as the energy radiated by a body per unit area, per unit time, within a specific narrow band of wavelengths. He defines the absorptive power, a capital letter A, as the fraction of incident radiation within that same wavelength band that the body absorbs. The core assertion of this section is that for any arbitrary body in thermal equilibrium, the ratio of its emissive power to its absorptive power is constant. Furthermore, this ratio is equal to the emissive power of a perfectly black body at the same temperature and wavelength. This claim, that the expression emissive power divided by absorptive power equals a constant value, constitutes Kirchhoff's law of thermal radiation. The evidence for this claim is entirely deductive, rooted in the inexorable logic of thermal equilibrium. Any deviation from the stated equality would imply a continuous flow of heat from a colder body to a hotter one, or vice versa, a direct violation of established thermodynamic principles. The argument's strength lies in its generality it applies to any material, demonstrating that the relationship is a universal feature of thermal physics, a conclusion mandated by the laws of energy conservation and entropy. Section 3. The universal function of wavelength and temperature. Building directly upon the previously established law, Kirchhoff makes his next profound claim: the constant ratio of emissive power to absorptive power is itself a function, and a universal one. This function, he argues, depends only on the wavelength of the radiation and the temperature of the body, and is entirely independent of the body's nature, substance, or form. He has shown that the ratio for any object equals the emissive power of a perfect black body. Since the black body's properties are by definition independent of material, its emissive power must be this universal function. This is an assertion of breathtaking scope. It implies that concealed within the phenomena of heat and light lies a single, fundamental mathematical relationship that governs the very fabric of thermal radiation itself. Kirchhoff's paper claims that the ultimate goal of radiation physics is to determine the precise mathematical form of this universal function. He does not, within this work, provide that form. The claim is one of existence and importance. He effectively lays down a challenge to the entire field of physics to find the equation for the black body spectrum. The evaluation of this claim reveals its foundational character. It transforms the study of radiation into a quest for a fundamental constant of nature, akin to the search for the gravitational constant. The intellectual framework he provides is robust. The existence of such a function is an ineluctable consequence of his thermodynamic reasoning. The paper's argument here elevates the discussion from a specific physical law to a guiding principle for future research, setting the agenda for decades of theoretical and experimental physics. The profound irony, discernible only with historical perspective, the successful description of this very function, Max Planck 40 years later, would require the invention of quantum theory, a conceptual revolution far beyond the classical world Kirchhoff inhabited. Section 4. Experimental verification. In the reversal of spectral lines, theory, however powerful, requires experimental validation. Kirchhoff proceeds to one of the most elegant and persuasive experimental claims in the history of physics. He focuses on the well-known phenomenon of the bright, double yellow line emitted by sodium when introduced into a flame. This constitutes the D line of the spectrum. The central claim of this section is that this specific, observable phenomenon provides a direct and visible confirmation of his theoretical law. He describes an experiment with a brilliantly simple design. First, he observes the characteristic bright yellow emission lines from a hot sodium flame. Then, he places this flame in the path of a much brighter light source that produces a continuous spectrum, such as a Drummond lime light. The critical observation, and the paper's core experimental assertion, is that when the continuous spectrum light passes through the cooler sodium vapor, two dark lines appear in the resulting spectrum at the exact positions of the previously observed bright emission lines. This phenomenon, which he calls the reversal of the spectral lines, is presented as irrefutable proof of his principle. The cooler sodium vapor, he argues, absorbs radiation far more powerfully at the precise wavelengths at which it would otherwise emit. The claim is that a substance's atomic or molecular constitution dictates a preference for interacting with radiation of specific frequencies, both for emission when hot and for absorption when cooler. The assessment of this claim must acknowledge its immense persuasive power. The perfect correspondence in the position of the bright emission and dark absorption lines provides a tangible, qualitative demonstration of the law that is immediate and convincing. It bridges the gap between abstract thermodynamic reasoning and concrete optical phenomena, making the universal law visible to the human eye. The almost theatrical quality of making bright lines vanish and appear as dark shadows lends the argument a weight that a purely numerical result might lack. Securing its rapid acceptance, Section 5, the cosmological application to the Fraunhofer lines, with his law established in theory and demonstrated in the laboratory, Kirchhoff makes his most audacious and far-reaching claim. He turns his attention to the heavens, specifically to the spectrum of the sun. For decades, the dark lines observed in the solar spectrum by Joseph von Fraunhofer were a catalogued curiosity, an unexplained set of markings on the light from our star. Kirchhoff's claim is that these Fraunhofer lines are nothing less than the reversed spectral lines of chemical elements. He posits that the sun is composed of a very hot, incandescent core, the photosphere, which emits a continuous spectrum of light, analogous to his Drummond light. This light then passes through a cooler, more tenuous outer layer of gas, the solar atmosphere, which is analogous to his sodium flame. The elements present in this solar atmosphere, he argues, absorb their characteristic wavelengths from the continuous spectrum of the photosphere, producing the dark absorption lines that Fraunhofer had meticulously mapped. He goes further, claiming a direct correspondence. By comparing the wavelengths of the dark D lines in the solar spectrum with the wavelengths of the bright emission lines of sodium from his laboratory flame, he finds a perfect match. The conclusion he presents is therefore a momentous one. The element sodium exists in the atmosphere of the sun. The strength of this claim rests upon the power of analogy, backed by precise measurement. The logical step of mapping his laboratory experiment onto the structure of the sun is a leap of breathtaking intellectual confidence. The evidence provided, the exact coincidence of the spectral lines, is compelling. This single claim dissolved the boundary between terrestrial physics and celestial mechanics, transforming the sun from a mystical object into a physical body subject to laboratory investigation. It effectively founded the field of astrophysics, demonstrating that the chemical composition of distant, inaccessible stars could be determined by a careful analysis of their height. Section 6, the foundation of a new chemical analysis. The paper's final, and perhaps most pragmatically significant set of claims concerns the application of these principles to chemistry. Kirchhoff asserts that the spectrum of emission, lines produced by an element, when incandescent, is a unique and unalterable property of that element, just as the sodium D lines are a fixed signature. He proposes that every chemical element, when sufficiently heated in a gaseous state, will produce a unique barcode of bright spectral lines. This signature, he argues, is so distinct that it can be used to identify the presence of that element, even in minute quantities or when mixed with many other substances. This claim establishes the foundation for the new science of spectral analysis, a method he developed in close collaboration with the chemist Robert Bunsen. The assertion is that spectroscopy provides a qualitative analytical tool of unparalleled sensitivity and specificity. The evidence for this was rapidly accumulating in their joint work, leading to the discovery of new elements such as cesium and rubidium, which were present in mineral waters in such trace amounts that traditional chemical methods have failed to detect them. The evaluation of this section's claim reveals its revolutionary impact on the practice of chemistry. It transformed the analysis of matter for a process of wet chemical reactions, precipitation, and titration into a physical measurement of light. It promised a method that was faster, cleaner, and orders of magnitude more sensitive. The internal logic is that if the spectral signature is a fundamental atomic or molecular property, as his theory implies, then its use as an identifier is absolute. This final claim brings the grand theoretical arc of the paper back to the laboratory bench, providing a practical technique that would redefine chemical discovery and analysis for the next century. In conclusion, Gustav Kirchhoff's 1,860 paper stands as a model of scientific reasoning, a tightly woven argument that progresses with sure-footed logic from a single theoretical postulate to a complete re-envisioning of chemistry and cosmology. The evaluation of its internal claims reveals a structure of remarkable coherence. The abstract idea of the black body provides the necessary foundation for a universal thermodynamic law. This law, in turn, finds its direct and visually stunning confirmation in the elegant experiment of line reversal. This laboratory of refined principle then becomes the key that unlocks the chemical secrets of the sun, bridging the terrestrial and the celestial. Finally, the principle of unique spectral signatures, a direct corollary of the entire argument, furnishes science with a new and powerful analytical method. Each claim builds upon the last, forming an unbroken chain of reasoning. Kirchhoff's work did more than answer questions, it established the very framework within which the next generation of questions about the interaction of matter and energy would be asked. Its true legacy lies in this complete and self-contained intellectual achievement, an edifice whose classical foundations were so solid that they would ultimately require the forces of a quantum revolution to be expanded upon.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.